Howdy folks, and welcome to the channel. In this episode, I've got a really hilarious tutorial for you guys. If you guys remember, in the previous episode, we kind of covered Petrel's geobody interpretation module, which actually extracts reflectors. Like whichever reflector you choose, you can just click on it and you can extract it. This was actually one of the routine procedures for seismic interpretation that is usually done manually, and it is extremely time consuming and subjective, as you guys know. And the thing about manual seismic interpretation is that by the end of the day, when you're done interpreting your seismic reflectors and other geobodies, when you go home, you see seismic reflectors all over the place, like on the walls, on the floor. Seismic reflectors are everywhere, and you can't just get it out of your head. That is the brutal reality of manual interpretation of seismic images, specifically 3D seismic images, right? But anyways, now having been through that hell that is interpreting seismic images, one of these horrible procedures is the fault interpretation procedure. Let's see how Petrel can handle fault prediction, and from this point on, it really gets worse for Petrel. Naturally, I used to do a lot of seismic interpretation with the seismic interpretation module. Then I kind of came across this new functionality, fracture modeling, that we have specifically with fault extraction module. So when I first saw this, I was like, hallelujah, we're saved. We don't have to look at these seismic reflectors all day. We can actually just automatically extract these faults. And this is something that you expect, as I said, right? So as you guys can see, we already have the Petrel application open and ready to go. And I've already gone ahead and loaded this seismic 3D image. So the reason behind this seismic image and why I chose it is that this image has got a clear strike slip fault with a clear direction, as you guys can see, right? And also let me show the inline and crossline sections as well. You can perfectly see the direction of the fault. This shouldn't be too hard for Petrel. If it actually can extract a fault, this should be a very easy task for it, right? Because there's only a single fault in this 3D image. So under the fracture modeling tab, we have the fault extraction module. Now let me see if I got this straight. It says open the dialog for automatic fault extraction. All right. Do you guys think this is going to actually salvage our soul and eyes, or do you think this is just a gimmick? All right, let's find out. Automatic fault extraction. Let's really do this by the book. So here it says input seismic edge volume. From seismology, we know edge volumes are attributes like chaos or variance, right? Now, let's take a look at this extra information here. Input and tracking volume, all right, so evidently it needs and tracking volumes. Drop an and tracking seismic volume or another edge enhancing seismic attribute as input for the automatic fault patch extraction process. So it either takes a and tracking seismic volume or another edge enhancing seismic attribute. What do you mean by that? Let me go in the hints tab. Let's find out. We can see that we have the input seismic, and we have this means volume attributes, okay? And this tells us precondition. What do you mean? It says variance and chaos. All right, so it needs variance and chaos. This looks like an ant. It says ant tracking volume, and here it says fault patches set, okay? So we can get either an ant track volume and get the fault patches from there probably, or we could directly get the fault patches from variance chaos. Now by fault patches, I presume it is the promised extracted fault plane, probably what it means by the fault patches set, hopefully. So let's do it. Now, I already have a realized seismic image here, okay? The one that is on display. So what we actually need is a variance or chaos. And potentially we also might need the ant tracking image. Let's see if we can create an ant tracking image and what we need for that. Ant tracking is used to extract faults from a pre-processed seismic volume. The pre-processing could be variance or chaos combined with structural smoothing. Currently only realized volumes can be calculated. Okay, so it's a good thing we already have a realized seismic image, and realizing seismic images is so easy. You just go in the realized modules, nothing. So, all right. So for ant tracking, we need a pre-processed seismic volume. It is chaos or variance with structural smoothing, no problem. So we have to start with chaos. All right, so I'm just gonna simply drop the seismic image right here, and then we're going to get our realized version of chaos, right? All right, what is the next step? It said structural smoothing, right? So let's get the structural smoothing. All right, no problem. Structural smoothing, and voila, we got the structural smoothing. Now, as promised, we should be able to get the ant tracking attribute. Am I right? So there we have the structurally smoothed chaos that we had. So apply, let's check. It says chaos, structural smoothing, and tracking realized. All right, we're done with that. Let's try it with chaos, since it says drop an ant track seismic volume or another edge enhancing seismic attribute, right? Okay, no problem. So this time we're going to drop the chaos volume here. All right, so there we go, chaos, and extract fault patches. Let's see how long it takes. All right, we're done with that, and we got the fault patches, right? We also have the ant tracking. I hope you guys are ready for the big reveal. Let's go ahead and see it. All right, so, all right, this is just crazy. This is ridiculous, guys. What the hell is this? I mean, we know that it's working because kind of the fault is there. You might see it, but what is all this junk all over the place? This looks like a preschool confetti project, really. We're not getting our money's worth out of this. But anyways, so let's just give it the ant tracking. And by the way, let's kind of look at it. I'm actually curious to see what it looks like. So apparently this is what it looks like. And we did exactly everything by the book, right? We created chaos, structurally smoothed it, then we did the ant tracking. All right, so here's the ant tracking version. Extract fault patches. Let's see how ridiculous this one is. All right, this is another level of ridiculous. I mean, honestly, the normal version was better. At least we were getting something out of this. But guys, this is not what you might expect from a $60 billion company, $100,000 application. But anyways, so guys, when I say commercial applications are actually struggling to keep up with the state of the art, that's exactly what I mean. Because this is clearly not using neural networks, right? And you guys saw how many hoops we had to jump through, right? Creating one attribute after the other. Like first we had to deal with chaos and then structurally smooth it. And then ant tracking. We were promised to get a fault plane, and we ended up with this miserable excuse for a fault plane. Now, let's see what our community-driven platform has to offer, okay? Since in SeismicFlow, we can easily use pre-trained neural networks. Directly, we can load neural networks, pre-trained neural networks into the platform. The state-of-the-art neural networks. Nowadays, people are working with 3D convolutional neural networks and their combination with attention mechanisms. That's a new thing. This is a 2024, 2025 kind of a deal. And it is the current state of the art, okay? Not like this Confetti project we got going on over here. All right, so as you guys can see, we already have the platform SeismicFlow ready to go. So we have the same 3D seismic image loaded up in the application. As you guys can see, it's the exact same image. and let me show you the fault. I think here I can show you better where the fault plane actually cuts through this 3D image, as you guys can see. So this is clearly the direction of the fault plane, right? Okay, and then take a look at here. The fault plane right here, then we have it just about here, right guys? And the coolest thing is that, take a look, moves. Do you see? Do you see it moving? So right here, they kind of join. See, this is where it is. And taking a look here, you can see it, right? So that's where we have our fault plane. Move it back. Let's start, you see, right here, and we have it here, right? So this is the data we're dealing with, the same exact image, all right? So what I'm gonna do here, okay, is I'm gonna go to the tools module of our very own community-driven platform, SeismicFlow, right? Here we have the geobody segmentation module, and the thing about making this application community driven was that you can actually use open source neural network models that were literally trained yesterday, right? Somebody, for example, published their neural network model on GitHub or Kaggle. You can simply download them and load it into the application and have it find the faults, right? So it's very simple. So geobody segmentation, here we go. I just have this 3D convolutional neural network model here. It's actually a unit. Let's see how it works. All we do is just to load it, give it the batch size. I think a batch size of 6 is good, depending on your GPU. So the thing about SeismicFlow is that it uses GPU acceleration. It's got native GPU support for TensorFlow and PyTorch. All you need to do is to choose the batch size you want that is kind of compatible with your hardware. 6 is good, I think. So let's see how it goes through. All right, we're done here. Now the thing about neural networks, and specifically using segmentation neural networks for image segmentation, specifically for these kind of binary tasks like fault prediction, like predicting foreground from the background, it is that we're going to end up with a 3D image that's got values between zeros and ones. So it's a probabilistic image. And since it is continuous, we need to actually threshold this, okay, to get a binary mask, right? And I kind of used the Otsu threshold method to find out the best threshold, and it is giving us 30%. So 30% is the optimal threshold here. All right. So now we got our geobodies, and we can simply see what it looks like. All right. Now we've got it. As you guys can see, there's a single fault plane exactly on the direction that we talked about, and it's cutting the image in the exact right places. So this is what I'm actually talking about when I talk about fault plane segmentation or actual automatic fault extraction. This is what I actually talk about. All right. So this kind of goes to show that how these commercial applications are actually struggling to keep up with the state of the art. All right. So that's it for today, guys. If you liked the video, please make sure to hit that like button, subscribe, and turn on notifications because we've got more of these coming. And as always, thanks for watching. Catch you in the next one.